breathe. And the chorus goes, sometimes all I need is the air that I breathe. However, you have to wait quite a long time for that chorus, which is why I find myself talking now. At the Science Jamboree, the air show was presented live to audiences of around 250 people. Children in the audience enjoyed helping me with some of the experiments. I could also ask the audience questions to make sure they were thinking about the science we were doing. Unfortunately, we cannot do a live show this year, so you are going to get a mixture of video and photographs. Some experiments have been filmed specially, but we had to do some of that outside for safety reasons. I hope you enjoy the show and learn some science. Now let's go back to that all-important chorus. Well, that's enough of that. But before we go on, I want a serious moment. I'd like you to read what is on the screen, listen carefully, and think about what you are hearing. If the Earth were a ball 1 metre in diameter, people would come from everywhere to marvel at it. They would walk around it, amazed at its pools of water and the water flowing between the pools. They would look in amazement at the creatures on its surface and in the water. But most of all, they would be fascinated by the very thin layer of gas around the ball. They would call this layer the air and would be amazed by it. They would marvel at how this layer sustained all that lived on the Earth. They would notice that there was one gas for the creatures and a different one for the plants, that it moved, carried water vapour, filtered out radiation and acted as a blanket to control the temperature. The air would be a great wonder, and people would do all they could to protect it, if the Earth were a ball 1 metre in diameter. So suppose we could go to a science centre or exhibition and see the planet Earth as a ball 1 metre in diameter. It would be a treasure that we would look after and protect. But of course, we don't look after our real world as we should.
So we all know that air is all around us. We've learned it in school, we've read about it, we just know it's there. But sometimes in science, how we know things is more important than what we know. And scientists are like detectives, they collect evidence to prove things. Now, what evidence could you find to prove that air is there and all around us? Children often say to me, if there was no air, we would be dead. And I say, yes, you're absolutely right, but have you ever done that experiment? I don't think so. So I'm looking for simple little demonstrations that you can do to prove to somebody that air is there. Here's one very simple one. If I take a glass and I put a tissue in, turn it upside down and put into my water, then many people will say to me that tissue will come out soaking wet. But of course, when we bring it out, the tissue is perfectly dry. Why? Because of course, air is there in the glass. Another thing we can do is that we can pour air. If I take one glass and fill it with water, and another one and turn it upside down, and then I can just tilt one glass and we can pour air upwards from one glass to the other, and we can see those bubbles, and there's really good evidence that we've got air there. Now, another demonstration I like, and I like to involve my audience, is to take a bottle with a balloon. The balloon is wrapped over the top, and I get children to blow into it. Now, blow. We can blow as hard as we like, we'll never blow that balloon up. But if I take this one, it's quite different. I can't blow that up because the bottle is already full. It's full of air. What about this one? What's my trick? You might guess it. There's a hole in the bottom. I blow the balloon up, air is pushed out, and the balloon can fill up and take that space. So, simple little evidence we see there, but here's some more. We're outdoors today, it's quite a windy day, but I like to use my leaf blower, and I like just to roll that around on the organ. And I'm imitating the wind. When air moves from one place to another, we call it the wind. And we can feel it, we can see its effect, and it's quite strong today. There we are, very simple evidence that air actually is there. Well, air is a gas, of course. No, it's not. It's a mixture of gases. And I wonder if you know which gases are in the air. How many can you name? Well, one I want to start with is carbon dioxide. There isn't much carbon dioxide in the air, but we use it quite often. Every time we open a can of Coke or take the top off a bottle of lemonade, we release carbon dioxide. But carbon dioxide is a strange gas, because when we get it really cold, it doesn't turn into a liquid, it turns into a solid. And I've got some of that solid with me now. Now, how cold do we have to get it? Way down to 0, and below 0, colder than your coldest freezer at -25, right down to -78 degrees C. And do you know what scientists describe that as? They say it is well cold. Now, I'm going to take some of that solid carbon dioxide and put it into this jug of coloured water. I wonder what will happen. Can you think what might happen now? Let's do it. I wonder if you predicted that. And I wonder if we could do it on a bigger scale. I wonder what would happen if we used hot water. Let's take some soap, some washing up liquid, and let's put in some hot water. And then in goes our solid carbon dioxide. Just a little bit, because this might be dangerous. Just a bit. Oh, no, not that much. Look out. Well, it is just bubbles of soap, and it's only carbon dioxide. It's quite safe. Let's put it out the way. Something else we can do with our solid carbon dioxide is to add some to these liquids here. What I've got in these liquids is a chemical called an alkali. And the colours are of substances we call indicators that show us by the colour that it is actually an alkali. And if I put some solid carbon dioxide in there and let it go, one's changed already, and so has the other one. They've changed colour. The colours indicate whether we've got an acid or an alkali. It started off as an alkali, and actually the yellow colour here shows us we've got a weak acid. Carbon dioxide in water makes a weak acid. Let's take those out the way. And finally, with solid carbon dioxide, let's take a rubber glove and take a little bit more here and pour some into my glove. Now, let's pull that out and tie a knot in the end. Oh, come on. And let's see what happens then. Let's just warm that up in my hands a little bit. There's the solid carbon dioxide in there, and I wonder if you can see what's happening. Can you see what's happening? Well, I'm sure you can. It's starting to blow up like a bit of like a balloon. The solid carbon dioxide is turning straight into a gas. It doesn't melt. A word we have for that is that it sublimes. Sublime, a nice word, meaning go from solid straight to gas. And because it doesn't melt, we call this substance solid carbon dioxide, we call it dry ice. And you might have met it before, and it's used a lot for special effects in theatres and shows. Well, another gas in the air is, of course, oxygen. It occupies about 20%, about a fifth of the air is oxygen. I've got some here today in a cylinder, and I'm just going to fill up a jar here with oxygen, and then we're going to use some of it. So just tighten up my valve there. There's all lots of oxygen bubbling out here. And why is oxygen so important? I'm sure you'll say to me, we use it for breathing. Well, yes, when we breathe in, our bodies do use oxygen. The correct name for that process is respiration. But there's something else that oxygen is really important for as well, and I wonder whether you can tell me what that is. And here's a little clue. It's burning. Nothing can burn without oxygen. So you might say breathing and burning. I would prefer you to say respiration and combustion. Now let's take a little stick and light it with my flame here. If the wind doesn't blow that out, and it is blowing it out. Well, the wind was blowing my lighters out, but here at the back now I've got a candle protected from the wind. I'm just going to light a little stick from it and get a nice flame, which I hope you can see. Now here's my jar of oxygen. I'm going to blow that flame out and put it in. It bursts back into life, and again, and again, and again. And not many people know that I hold the world record for lighting a splint like this in a jar of oxygen, 32 times in one jar. Well, I won't get there today, but you see what's special about oxygen. Things burn brighter, things burn faster, things burn more fiercely in pure oxygen than they do in the air. And some things that we wouldn't expect to burn will actually burn in pure oxygen. So wood will burn, plastic will burn, paper will burn, but not metal. Now, if I take some iron, fine iron wool here, and I take my flame again and quickly put this in the flame and into the jar of oxygen, we get some nice sparklers as the iron actually burns there in oxygen. Well, we burn so many things, of course, that we take for granted that fire requires oxygen. And whenever we travel in a vehicle that uses petrol or diesel, we will be burning things and we will be using oxygen. I can't show you inside a car engine, but my bottles will imitate that. I'm not allowed to use petrol or diesel, but here's a liquid a little bit like petrol. Let me pour some in there. And another liquid, also a little bit like petrol, a diesel, a fuel, I'm going to put in there. Now, when petrol goes into a car engine, the first thing that happens is it gets warm and it evaporates. And I'm going to shake this up and I'm warm it up with my hands, and this one the same. Shake it around, get some of that liquid to evaporate. I want to fill up the bottle with vapor from the fuel, and of course it's mixing with air that contains oxygen. So shake that all around, shake this one around, and then I want to pour out the liquid that has not evaporated. There's one. There's the other. And then we're going to set fire to them. Let me put those liquids away safe. And candle has gone out. Let's try and light that again, because we need a flame and I need to be some distance from those bottles. So, here we go. Let's light my little stick again. Blown out. One, whoosh. Two. Oh, not quite so good. We call them the whoosh bottles. And those sorts of little explosions happen over and over again in a car engine. At the end, it's full of exhaust gas, but also some liquid that will be water that comes from burning those fuels. So we show you there the importance of oxygen in combustion. Well, air stretches way, way, way up above us. What you probably don't realise is that you live at the bottom of an ocean of air. And all that air up above us actually weighs something. Like all substances, air weighs something. And it's weighing down on us now. You young people don't appreciate the load that's on your shoulders. Now, air pressure is big stuff. And I'm going to show you some demonstrations to emphasise that. First of all, here's a little demonstration that you have to do yourself. It is your science homework for tonight. You take a glass and a bowl or a sink full of water, a piece of card, and you put your glass into the water, fill it up, bring it out with the card, and hold it all up and simply let go. Now, ever so easy to do, you've got to do it. And we take the card away, of course it all falls out. Now, what's holding the water up? Why doesn't it fall? The answer is air pressure. Air is pushing down harder than that water is pushing. So I wonder how hard it is pushing. Could I use a bigger jar? What about this big one here? If I put that in, and I took my lid there, I wonder whether air pressure will hold up all that water. There we go. Let's hold it up. Yeah, no problem at all. And in fact, air pressure is so big, if that jar was 10 meters tall, the air would still hold it all up. So air pressure is big stuff. And I'm going to show you two more demonstrations now. I want a volunteer to get into a black plastic bag for me. Right, just walk on the spot a moment. We're going to pull that up around you. And I've got a vacuum cleaner here. And I'm going in there. Got this side there. Just we're going to gather it tight around his neck and make it airtight at the top here. Yeah? Oh yeah, keep it going. That's better. How are you feeling? All right? Can you walk? Not very well. Yeah. Does it remind you of anyone? Who? Is he? There we go. There, out we come. Thank you. Big clap, please, for Batman. And then I want to tell you a story about a very famous man from many, many years ago. He lived in Germany, the mayor of a little town called Magdeburg in Germany. And he was called Otto, and he liked to do experiments. And one day, he went to the blacksmith and he got the blacksmith to make him two metal hemispheres, halves of balls. And he got them and he took them home and he put them together and he sucked the air out from in between them. Now, that's easy for me to say and pretty easy for me to do because I've got a nice modern handheld pump here. And Otto didn't have a pump. He had to invent the world's first vacuum pump. And when he had sucked all the air out from in between them, then he disconnected his pump and tried to pull them apart. Now, that's much more impressive if I have somebody to help me do it. Pull it apart. Oh, I just put it together. Pull, pull. Go on, Martin, pull. Oh, well, they tried this. They tried it. They couldn't get it apart. So the guy thought, I wonder what I can find that's stronger than my friend Martin. It's a long time ago, 350 years ago. What's the strongest thing they could have to pull? Horses. Yes. Martin, you are a horse. Can you make a noise like a horse? Nay. Oh, okay, just about. Go on. I'm a horse as well. We are now two horses. Pull, like two horses, but pull, 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 pull. Two horses pulled as hard as they could. And guess what? They could not get it apart. So he thought again. I know what. He got two more horses. Then another two. And then four more. And two more after that. And I've lost count. But he ended up with 8 horses each side. Now, his hemispheres were a bit bigger than mine. But there we are, 16 horses were pulling this. Mine, you've been messing about so far, right? I want you to pull seriously now. Yeah? You are 8 horses, I am 8 horses. We're going to pull this apart. Go on, 16 horses pulled, and pulled, and pulled. And you can guess it, can't you? They could not get it apart. And they could not pull it apart until he did this. Listen. Shh. You'd heard that at the front. Wasn't you, Martin, was it? No. Go on. And there we go. Big clap for our horse, please. So let me give you some science, some good science. A long time ago, a famous scientist called Daniel Bernoulli simply blew across a piece of paper. And blowing on a piece of paper, he thought would push the paper down. But what happened? The paper came up, and he discovered a really important bit of science. A moving gas that I'm blowing across the paper doesn't push as hard as a still gas underneath it. And that's Bernoulli's principle, and really important because although he never lived to see it, it is the principle that explains how aeroplanes fly. Now, we remember Bernoulli with this little arrangement. Simply a hairdryer and a balloon. Now, if I tilt that hairdryer, then it doesn't look as though that should happen. But every time the balloon tries to get out of the moving air, the still air pushes it back in. Back we go. And on a good day, I can get 2 balloons in there. Yes. 2 balloons floating, and that's Bernoulli's principle. You can try that at home, certainly. Well, I like doing that, but I would like to do it with a big balloon. Have we got a big balloon? Well, remember that glove that we filled up? That's quite a big balloon, isn't it? There's white frost on the bottom, and there's a bit of snow. Well, There's still a bit of dry ice inside there. Not all sublimed yet. But no, I want bigger than that. And this is what I call a big balloon. Now my hairdryer will never get that off the ground. And when the wind stops and when the weather improves, I'll go outside with my leaf blower and we'll get that up in the sky. You remember when I blew across that piece of paper? Which way did it go? It went up. What if we blow across a long piece of paper? Here's a long piece of paper, and here's my blower. Let's try. Here's one of my favourite demonstrations. It's science from two French brothers that they did years and years and years ago. They were called the Montgolfier brothers. But I'm sure you speak French, so you would understand les frères Montgolfier. What they did was to take big material cloth bags and fill them up with smoke. Well, they didn't need the smoke that made everybody cough and splutter. And here's my version of it. We wanted to do this outside, but the wind is too strong. Let's try it here. So all we've got is a hairdryer filling up this big plastic bag, and up, 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 up it goes. We've got a hot air balloon. You don't need smoke, it's just hot air. Now, why does it work? When air gets hot, it expands. We can get less air inside the balloon. We know that air weighs something, and the balloon is lighter because the air has expanded. We've done this at many jamborees, and I'll show you some photographs of other hot air balloons we've made.
Here I am in my local park on a nice sunny morning with my 15-metre long solar bag. Spreading it out and filling it with air proved more difficult than I expected. I didn't like having to run around to fill it up, but we got there. It is important to stay out of the shade and get the bag heated by the sun. So here we go, back into the sun, the bag gets heated, and we have liftoff. I love it, and I'm coming back tomorrow for another go. I need to get the bag even more full of air and attach it to a long string. I also need to stay well away from the trees. To finish the air show, we wanted an exciting ending that would show again some of the key ideas from the show.
If you are of a nervous disposition, try to figure out what you might do, because you aren't getting anything else on health and safety from me. Here we go.
We looked around for a piece of equipment, but couldn't find anything. Then we got an idea from this guy. What we made might look like an old piece of plumbing, but actually it's a sophisticated piece of scientific equipment.
We start by taking a ball of paper and dropping it in the muzzle. We take the special rammer and we ram it down. We take our secret rocket fuel and we spray a little bit into there. And then we attach the firing mechanism, and there might be a slight pop. Let's see if it's going to work. There we go, 1, 2, 3. Shall we try that again? You know how to do it. We take a piece of paper, we screw it into a ball, we drop it in. We take the special rammer and we push it down. We just test the lighter mechanism, yes, and we take the secret rocket fuel. That was more like it, wasn't it? That was more like it.